Hello, I'm Anna Rose, and today I will be showing you how to find the Eigenvalue and Eigenvectors of a matrix. But first, I will show you how to find an Eigenvalue. So for this first one, it's pretty simple. We can use this triangle method to find the Eigenvalues because under it we have all zeros. So the Eigenvalues would be 1, 0, and 4. When you have an Eigenvalue of 0, automatically the matrix is not invertible. And that will stand for all matrices. Every time you have a 0 as an Eigenvalue, it will never be invertible. Also, I forgot to add that the matrix is diagonalizable because it does have a multiple of 1 for each value. In other examples, we'll see where they don't have a multiple of 1, and then I will show you how to make sure that they are diagonalizable. Okay, so for this matrix, I will also show you only how to find the Eigenvalues. So for this one, we can't use the triangle method because there's not, zeros completely on one side of the triangle. So instead, we're going to have to use this method that I will show you. So diagonal, like for here, you're going to, on each spot, take that number and minus it by Eigenvalue, and then keep everything under it. So then 5 minus Eigenvalue, 0, 3. 3 minus Eigenvalue. And same thing, kind of like how you do the determinant, you can do it the same way for this. So those would just become zeros. We don't have to worry about that. So we can take the 3 minus Eigenvalue and put it in here and make a mini 2x2 matrix. -4 minus Eigenvalue, 5 minus Eigenvalue, plus 18. All right, so we're going to have to simplify this out, which is going to be -20 plus 4 Eigenvalue minus 5 Eigenvalue plus Eigenvalue squared plus 18. So now this is going to be 3 minus Eigenvalue, which is 1 on its own, Eigenvalue squared minus Eigenvalue minus 2. So to simplify that, we should be able to do 3 minus Eigenvalue, Eigenvalue, that should be a 2 and a 1, and it will be a minus and plus. Perfect. So our final Eigenvalues would be 3, 2, and -1. And all of them have a multiple of 1. Our next example, we will show one where they aren't multiple of 1s. Okay, so for this one, we will have multiples of more than 1, which we have to make sure that the matrix is diagonalizable. And we will also see if we can diagonalize this matrix. Okay, so again for this one, it's a pretty big triangle, but we can use that triangle method. And we get Eigenvalue of 4, multiple of 2, Eigenvalue of 3, multiple of 2. So to see if it's diagonalizable, we're going to have to diagonalize the matrix and find the Eigenvalues of it, which we will also do. So we will first start with 4, okay, with 4. So when you start with it, how you're going to do it is, again, so this diagonalized part, every time when you try to find the Eigenvalues of a matrix, or, even try to find if it's diagonalizable, which we're going to do in both, you're going to have to take this value right here and then minus it by your Eigenvalue. So since we're doing 4, it's going to be 4 minus 4, which is 0. And put the rest of the values under it. Okay, and then the next one here is 3. So it would be 3 minus 4, which is -1. and then put the rest of the values under it. Then the next one is going to be 3 again, and again that's going to be -1. And then for the last value, it's 4, which again, 4 minus 4 is 0. Okay. So let's change up the order a little bit because we have the first row all of zeros. So let's put that one at the bottom, and then let's put the second one at the top. 1, 0, 0, and then the rest can just stay the same. 0, -1, 5, 0. Okay, perfect. So the next part will be doing the second one. 0, -1, -1, 0. We're going to try to put it in row reduced echelon form. So let's positive that whole line. So then add them together. It's going to be 0, it's going to be 1, and it's going to be 0. Add them together. That's going to be 0, it's going to be 0, it's going to be 6, and it's going to be 0. And then just keep the lower one the same. 0, 0, 1, 0. I just simplified this and divided them all by 6, which gave me 1, 0, 1, 1, 0, 1, 0, 1, 0. Okay. Now let's do the third row. That is going to be 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. So we have one free variable. This is how you're able to find if it is diagonalizable. So you're going to see the number of multiples for your ing values, and that has to be equal to your number of free variables. So our number of multiples for our ing value is 2. And is that equal to our number of free variables, which is only 1? No. So it is not diagonalizable. Okay, but we can finish though to see the ing value, which is pretty simple. Our matrix with these is going to be x1 is equal to 0, x2 is equal to 0, x3 is equal to 0, and x4 is equal to x4. So we can just take the x4 out, and that is going to be 0, 0, 0, 1. And that's the ing value. And that is all of our final answers for this problem. Now we will find the ing vector of 3. Okay. So for 3, it is going to be kind of like 4. So 4 minus 3 is 1, 1, 0, 0, 0. 3 minus 3 is 0, 1, negative 1, 0, 0. And again, it's going to be 0 because 3 minus 3, 5, and then 0, 0. 4 minus 3 is 1. Okay. So same thing, we're going to try to simplify it to row reduced echelon form. This is going to be easy. This line right here is going to be all zeros because it's practically the same line. And then you're going to have 0, negative 1, 0, 0. Turn this into a positive. 0, 0, 5, 1. Now we are going to do the final line. 5, 1, but divided by 5. And I have 1 over 5. And that is going to be it for doing row reduced echelon form. I can switch the order, but I technically don't need to. You can just do it to understand it better. But I will show you how you can do it. x1 is equal to 0. x2 is equal to 0. x3 is equal to negative 1 over 5 x4. And x4 is equal to x4. So it's x4, x4, it's going to be 0, 1, 0, 2. 3 is going to be negative 1 over 5, and 4 is going to be 1. Then when you can simplify it by multiplying everything by 5, that is going to be 0, 0, negative 1, and 5. And that is your Eigenvector final answer. Okay, so this is our last problem for today, and for this one we will be finding the eigenvalues and the eigenvectors. Okay, let's get into it, just like last time. To find the eigenvalues first, you're going to have to minus them by the eigenvalue symbol, minus eigenvalue. Now do it just like you would do a determinant, multiply, cross multiply practically, so 9 minus eigenvalue, 5 minus eigenvalue plus 4. 9 times 5 is 45, minus 9 eigenvalue minus 5 eigenvalue plus eigenvalue squared plus 4. That's going to be eigenvalue squared minus 14 eigenvalue plus 49. That's pretty simple. That is going to be 7 and 7. And minus, so that is going to be eigenvalue 7 multiple 2. And again, to see if it is diagonalizable, you're going to have to, and we can check for that as well, you're going to have to make sure that the number of multiples of the eigenvalue, which is this right here, has to equal the number of free variables of the matrix. Okay. So now we found our eigenvalue. Now let's find our eigenvectors. So again, same way, we only have 7 and a multiple of them 2. So that is going to be 9 minus 7, 2, 2, negative 2, and 5 minus 7, which is also negative 2. This is pretty simple since these two rows are exactly the same. It's going to be 0 on both. You can simplify the first row, which that'll be 1, negative 1, 0, 0. So there is one free variable here. So it is not diagonalizable because there are 2 multiples and only one free variable, and they don't equal each other, so it's not diagonalizable. Now let's find the eigenvector. That's going to be, there we go, that's going to be x1 is equal to x2, and x2 is equal to x2. So x2 is equal to 1, 1. Multiplied by 1, 1. And that is your eigenvector. Thank you for following my video and being here all the way to the end. Please like and subscribe, and thank you so much for your support. It means a lot.